So hello everyone. In this one we're going to be looking at CSEC question 9 questions. Um, so you would find a lot of circle geometry questions here, and then in the second part of the question you would find bearings, right? So I just want to point out to you what this question usually uses. So for the circle geometry part of it, you would use the circle theorems, which are these. So we have the first one where the angle in a semicircle is 90 degrees. So once you have a diameter, and then you have an angle that is going from a diameter to the circumference, that angle is going to be 90 degrees. Here you have the angle at the circumference is half the angle at the center. So if you have an angle that going to the circumference of a circle, so it's going to the circumference of a circle and going to the center of the circle. Notice they're coming from the same point or subtended by the same chord. It might usually be a chord across there. Then the angle at the center is going to be twice the one at the circumference. And the third one, which is this one here, we have the same kind of situation with a chord and two angles coming from the same chord. So we've got this chord here, and then this angle here, and this angle here coming from the chord going towards the circumference. So once two angles are subtended by the same chord at the circumference, you find that those angles are equal. It kind of gives you a butterfly effect if you look at it. The fourth one would be the opposite angles in a cyclic quadrilateral are 180. So once you have a quadrilateral within a circle where all 4 points are touching the circumference, then that's considered to be a cyclic quadrilateral, and the opposite angles are going to sum to 180. So they're supplemental angles, they sum to 180. So 100 plus 80 is 180, and 110 plus 70 is 180. The next one we're going to have is this one here, where the angle between a radius and the tangent is 90 degrees. So we have this tangent here that is touching the circle at one point, and then we have a radius that is coming from the center to that tangential point right there, and the angle between those are going to be 90 degrees here. The next one we have is the alternate segment theorem, where the angle between the chord and the tangent is equal to the opposite angle inside the triangle. So we have this tangent that's coming here, and if we look at this chord here, the angle between there is that chord and the tangent is 60 degrees, and then the angle in the opposite angle inside the triangle, which would be here, would be 60 degrees. So look at the chord and then the angle that that chord makes inside of the circle at the top, right? So the chord forming the base of your triangle, that angle is going to be 60 degrees. And if we look at it on the other side of the chord, other side of the tangent, we have this angle of 70 degrees here, and then we have this chord coming here. And if this chord now is the base of the triangle, then the angle at the top is going to be the opposite angle inside, and that is going to be equal to 70 degrees there. The next one we have is the one to the bottom left, where the tangents to a circle from the same point will be equal length. So if we have two tangents that are coming together at a point, then the length from D to C would be the same length as D to E. So this distance here is going to be the same as this distance here. And finally, the radius through the midpoint of a chord will bisect a chord. Bisect means to cut it in half. So if you have a radius that is going through the midpoint of a chord, so it's not just a radius passing through a chord, it has to be the midpoint of a chord, then that radius is going to be bisecting the chord at 90 degrees. So you're going to have a 90-degree angle there. So those are the circle theorems we're going to be using mostly here. And then, of course, you're going to use some triangle properties as well. A common one is isosceles triangle. A very, very common one you would find is that they give you a circle, and you have two radii, and then they have a chord coming here. This makes an isosceles triangle, which means your base angles are going to be equal. That's pretty common as well. And yeah, that's usually the triangle that you get there. So now we're going to look at some formula that we're going to use for the bearings part of your questions. So I'm going to open up a CSEC paper that has the formula sheet. Now, usually this sine rule and cosine rule below here, this is what is the basis of your bearings questions. Of course, you're going to still have to use some angle properties as well, knowing your 180-degree angle, 360-degree angle. Also bearing in mind that when you are doing a bearings, it always measure from north and counts in a clockwise direction. Your angle is always measured in a clockwise direction from the north arrow, right? So make sure that you know your sine, your cosine rule and your sine rule. Become familiar with it and be able to apply it in the questions, and you would see as we go along how we can use it. So good, let's look at the question 9. So we're just going to do a couple from the sheet. I'm not going to do all of them. So we're going to start with this one. Sorry about that. So reading the question, H, J, K, L, and M are points on the circumference of a circle with center O. M, K is the diameter of the circle, and it is parallel to H, G. Okay, we're told that MJ equals to GL, so we can see that by these little lines here, and we can already know that we have an isosceles triangle. MJL is going to be an isosceles triangle, and we're told that angle GMK is equal to 38 degrees, and we can see that on the diagram. So we wanted, first question is to explain, giving a reason why angle HGM is 38 degrees. So angle HGM. So because we have these two parallel lines, HG is parallel to MK, and then we have a transversal coming across here, it means that this angle and this angle are alternate angles. So that's going to be your reason. Your reason would be angle HGM and angle GMK are alternate angles. Right? So that's going to be our answer for that. All right, and then why is angle MGK equal to 90 degrees? So angle MGK, so MGK, if we look, we have a diameter here, MK, and then we have this MGK is an angle in a semicircle, which gives us 90 degrees. So angle MGK is an angle in a semicircle, which is 90 degrees. All right, so that's that. Let's clear that up and let us continue. All right, so we're to determine the value of each of the following angles and show detailed working where appropriate. So we want angle MLG, so that's this angle here, and so we just found out that here was 38 and we have 90 up here, right? We want to find out angle MLG. So angle MKG, which is here, we can figure that out. We can figure all that out. We're going to start there. So angle MKG will be equal to 180 minus the sum of 90 plus 38, right? Because we have this triangle here, triangle MGK, where we know 38, we know 90, so we can figure out the third angle. And this works out to be 52 degrees. Now, if we look at the chord MG, we have this chord MG, and then we have the angle at K and the angle at L, both coming from that chord. So therefore, we have angles being subtended by the same chord. So therefore, those two angles are going to be equal. So we've got angle MLG is equal to angle MKG, which is 52 degrees. And our reasoning we would give is that angles subtended by the same chord are equal. All right. Okay. Next, angle LKG. So let's see if we can find angle LKG. Clear this up. Right. So in triangle MGL, we have that LMG is equal to GLM because it's an isosceles triangle, right? So we've got GL. So this is an isosceles triangle, so therefore we have this angle and this angle being equal here, right? So therefore we can figure out, so we just found out that this angle MLG is 52. We just worked out that this is 52, which means this entire thing here is 52, which means we can figure out this bit here by taking away 38 from 52. So we can say angle LMK is equal to 52 degrees, take away 38 degrees, which is equal to 14 degrees. So we've got here being 14 degrees. Nice. Now, if we look at the chord, if we look at it's not really a chord that's there, but it's an imaginary chord, but they're coming from the same position. So angle LMK and angle LGK are coming from the same chord, so therefore here is going to be the same 14 degrees, right? So we can see that this angle is coming from there, and then this one is coming from the same position, so therefore we get the butterfly effect there, and therefore they are both 14 degrees. So we can say angle LKG is equal to angle LMK, which is equal to 14 degrees, since they are subtended by the same chord. Right. And then angle GHM. Let's see where angle GHM is. Angle GHM Okay, so there's a cyclic quadrilateral here. If we look at here to there to there and back to L, there's a cyclic quadrilateral there, and we know the rule where opposite angles in a cyclic quadrilateral are equal. So therefore, angle JHM would be equal to 180 degrees minus 52 degrees, which is 128 degrees. And of course, we have to put in our reasoning, which is opposite angles in a cyclic quadrilateral are supplemental, meaning they sum to 180 degrees, right? SUPPLEMENTEL. Right. That's your reasoning there for that. Moving on to the bearings question. From a port L, from port L, ship R is 250 kilometers on a bearing of 065 degrees. Ship T, very important, anytime you have to write your bearing, make sure that you have 3 digits of for your bearings, right? So even if it's like 65 degrees, put a 0 before it to make sure that it's 3 digits. Bearings are always given in 3 digits. So from a port L, ship R is 250 kilometers on a bearing of 65 degrees. Ship T is 180 kilometers from L on a bearing of 148 degrees. This information is illustrated in the diagram below. We have to complete the diagram above by inserting the value of angle RLT. So angle RLT is this angle right here. Now we're told that the bearing from L to R is 065 degrees. So we're starting from L, the north arrow at L, we're going in a clockwise direction to R, and we're going to get here is going to be 065 degrees. And then we are told that ship T is 180 kilometers from L on a bearing is on a bearing of 148. So remember, it is from L, right? It doesn't continue from where we stopped for R. It's coming from L, and this is going on a bearing of 148 degrees. So this here is 148 degrees to T. Right, and now we're being asked to complete the diagram above to insert the value of angle RLT. So now if we have that whole angle is 148 and this bit inside here is 65, then therefore inside here is going to be 148 minus 65, which works out to be 83. Right, and your task was to write in that angle, so of course you make sure you come and write it in on the diagram. So 083 degrees. We're to calculate RT, the distance between the two ships. Now we've got 2 lengths, LR and LT, and we're being asked to find the third length, RT, and we have an angle. Whenever you have a triangle that you have to find a side or an angle and you have 3 lengths involved and only 1 angle, that is automatically the cosine rule, right? So using the cosine rule, we have that RT squared will be equal to LR squared plus LT squared minus 2 by LR by LT cos of the angle at L, right? So I'm just going to put cos of angle L. So we're trying to find the distance RT. So that distance, the square of that distance is equal to the square of LR. LR plus the square of LT minus 2 times the length LR times the length LT times cos of L. So substituting our values, this would be equal to 250 squared. What just happened? Oh, right. $250 squared plus 180 squared minus 2 by 250 by 180 cos of the angle we just found, which is 83. Yes. Punching this into your calculator works down to be 83931.75909. Now this is RT squared. You're being asked to find RT, so therefore we need to come and find the square root of this. And this works out to be 289.71 kilometers, and we work that to 2 decimal places. So that's that, using the cosine rule. Now remember that the formula sheet is given at the front of your paper. So if you don't remember the rule, all of the elements of the rule, just look in your formula sheet, get the formula. If you need to relabel your triangle as you do it to match the formula, then by all means go ahead and do that, but you have to become familiar with how to use the formula that is given to you. Part 3 is asking us to determine the bearing of T from R. So now we're going to start at R. So always put in your north arrow. So I'm going to put in my north arrow. And we're going to find our bearing of T from R. So we want to go down to here and find this angle. Now, in order for us to be able to figure out that angle there, we need to figure out the rest of the entire circle angle, right? So we can figure out this bit here because we have 2 north arrows. That means they're parallel, and of course we can have 2 internal angles here. So this angle here and the 65-degree angle here will sum to 180, so we can figure out this angle. This one here is going to be 180 minus 65 degrees, and that is going to work out to be 115 degrees, right? So that's 115 degrees. For the angle on the inside, we can use the sine rule. So now, this one is when you have 2 angles involved in your triangle. All you need are 2 angles and 2 lengths. Now, even if you have 3 lengths, that's fine, but once you have 2 angles, you can use the sine rule, right? So the sine rule states that the ratio of a length and the opposite angle is equivalent to the ratio of another length and its opposite angle in your triangle. So therefore, we can use, if we want to figure out this angle here, we can use the opposite side, plus we have this angle 83, and we can use the opposite side to that angle as well. Right? So we're gonna find that the 180 over sine of angle R will be equal to 289.71 over sine of 83. Now remember, we just worked out this length and we found it to be 289.71 kilometers, right? So we're using that length with the 83 opposite, and then the length of the 180 with the angle that we're trying to find opposite to it. So we're gonna rearrange this to get sine R. So sine R would end up being 180 sine of 83 over 289.71, and this works out to be 0.6166798 1. But we want to get the angle at R, so we're going to get sine inverse of that figure. And we got our angle at R there is 38 degrees. So we have that here now is 38 degrees. So we've got up above being 115 and here being 38. We can now find out the bearing of T from R. So our bearing of T from R will be equal to 360 minus the sum of, let me do that on the next line. What is going on here, man? All right, on the next line, right? So that's going to be 360 minus the sum of 115 plus 38. So this is going to work out to be, let me see, 38 plus 115 is 153. I'll take it to 360, and this is 207 degrees. That's 207 degrees. So that's that question. I'm gonna do one more. I'll do one more question for y'all. This one is an easy one. We've got the diagram now drawn to scale, shows a circle. The points P, Q, R, T, and V are on the circumference. QRS is a straight line. Angle PVR is 75 and angle TRS is 60. Now, point to note, this line QRS is not a tangent. Right, although you see it sticking out and there's an angle between tangent and between that line and the chord, that is not a tangent. Okay, so please do not make that mistake of taking it for a tangent and applying the rules with tangents to that line. So the first part is asking us to determine the value of each of the following angles and show detailed working where necessary. Give it a reason to support your answer. So we want to first find angle PTR, which is this angle here. And firstly, we can see that angle PTR and angle PVR are coming from the same points. So angles subtended by the same chord. So therefore here is going to be 75 degrees, right? So you would write in your answer that angle PTR is equal to angle PVR, which is equal to 75 degrees. And your reason would be that the angles are subtended by the same chord. The next part of the question is asking us to find angle TPQ. Angle TPQ, which is, let me just clear this up here. All right. So angle TPQ would be this angle right here. And for that angle, if we look at, we can first, angle TPQ is part of a cyclic quadrilateral, right? So if we look at PTRQ, that makes a cyclic quadrilateral. So it's a quadrilateral that is touching, its 4 points are touching the circumference. So if we look at, if we try to find out this bit here, then we can get the opposite angle, since opposite angles in a cyclic quadrilateral are supplemental, meaning that they sum to 180 degrees. So we have a straight angle here, and we have this bit equal to 60 degrees, so therefore we can figure out that this bit here on the left is 120 degrees, right? So 180 minus 60 is 120 degrees. Now the opposite angle will therefore be equal to 60 degrees because they have to sum to 120 degrees. So you're going to show that angle TRQ is 120 degrees, or you can actually show the working 180 minus 60 degrees and give the reason that a straight angle is equal to 180 degrees. Then you can show that angle TPQ is 180 minus 120, sorry, which is 60 degrees, and your reasoning will be that opposite angles in a cyclic quadrilateral are supplemental. Next, we're being asked to find the obtuse angle POR, where O is the center of the circle. Now this wasn't shown in the diagram, but I'm going to draw it in. So let's assume the center of the circle is about right there, and I'm going to draw two lines, P, O, R. Now P to O and O to R are going to be two radii, and if we again imagine this imaginary chord here, we can see that angle PTR, which is this angle up above here, up by T, and then angle POR, which is the angle of the center, are coming from the same points P and R, or subtended by the same chord. And then there's a rule where when you have an angle of the center of the circle, it is 2 times the angle at the circumference when it is subtended by the same chord. So therefore, this angle at the center O is going to be 2 times 75, which is going to be 150 degrees. So you're going to put in that angle POR is equal to 2 times angle PTR, which is 2 times 75, which is 150 degrees. That's going to be your working. And then you're going to put for your reasoning that angle at the center is 2 times the angle of the circumference when subtended by the same chord. That was a pretty simple one. And part B, we have this diagram. This one is an angle of depression question. This one also uses the sine and cosine rule, but it also uses some trigonometric ratios as well, right? The SOHCAHTOA. So you have to be familiar with those as well. So a person at the top of a lighthouse, TB, sees 2 ships, S1 and S2, approaching the coast as illustrated in the diagram below. The angles of depression are 12 degrees and 20 degrees respectively. The ships are 110 meters apart. And we're to complete the diagram below by inserting the angles of depression and the distance between the ships. So we're told that the angle of depression, remember, angle of depression is where you're standing up and you're looking down, right? So therefore, we're going to have between T, the eye level, and S2 and TS2, we're going to have an angle of 12 degrees. And then we're going to have an angle of 20 degrees between the eye level and TS1, which therefore means that we have an angle of 8 degrees in this space here, because 20 take away 12 is 8. All right. Now we're being asked, we also have to show the distance. Yeah, and the distance from here, from S1 to S2, is 110 meters, right? So we have to show that as well. Okay, some other important things to note is that this full angle here is going to be a 90-degree angle, which then means we can figure out what this angle here would be. Since it's 20 degrees out there, here it's going to be 70 degrees. The 70 add 20 is 90. All right. And then we can also figure out that, because we have eye level and the ground level being parallel, we can figure out that here will be 20 as well, based on alternate angles. So if we have two parallel, and then we've got the transversal coming between parallel lines, then this angle and this angle will be equal. So for S1 it will be 20, and for S2 here is going to be 12 degrees. So just some things you can fill in there from the start. So the next bit we're being asked to find out is the distance TS2 between the top of the lighthouse and the ship 2. So we are being asked to find the length of this line here. And we've got a little triangle in between there. I'm going to re-sketch it. So if we look here, and then we have this bit coming up here, and then this bit coming down here. Here is 110. This is S2. 2. This is S1, and this is T. We know this angle here to be 8. We know this angle here to be 12. And we can then know that this angle here is going to be 160, because I mean it's a triangle after all, right? Here will be 160, because here is 20 and this is a straight angle. Here would be 160 degrees. So that was 160. Let me see if I can draw this a little better to be a little clearer. Right, so we've got down here, we've got this bit going up over here, and then we have this bit coming down here. This is S2, this is S1. We have 110 here, 12, 160, and 8, and this up here is T. Right, good. We could work with that. So we want to figure out the length of ST. We already have one length, so we can use here the sine rule or the cosine rule, because we have all of the angles, and we have at least one side and we have another side involved. So two sides involve two angles. I think the sine rule is an easier rule to use, so I'm going to use the sine rule for this one, right? So using the sine rule, we will get that TS2 over sine of 160, because we have to use the angle opposite it, would be equal to 110 over sine of 8. So that TS2 is going to be equal to 110 times sine of 160 over sine of 8. Again, remember to make sure your calculator is in degrees when you're working this out. This works down to be 270 meters in length. So we've got that this length here is 270 meters. The next part of the question is asking us for the height of the lighthouse TB. Now if we look at the triangle, so they're asking us now for this height here, TB. So let's see. We have the length of TS2. So if we look at this whole triangle here, we're gonna just sketch out the whole triangle from TBS2. We're totally ignoring S1 for now. So this is not working the way it's supposed to. So let me see if I can get a proper triangle here. Alright, so we got T, B, and S2. We know that 70 plus 8 would be 78, so this one here will be 78. Okay, because we're dealing with this triangle here, we're dealing with this length TB, and this length TS2 and this length BS2. So therefore we have to take this entire angle there, which is 78 degrees. We know that this angle over here is 12, and we know this is a 90-degree angle, and we want to find out the length of the, oh, we also worked out that this length here was 270 meters. All right, so what can we do? We can do one of two things. In fact, we're just going to use sine. Yeah, because we have the hypotenuse and then we're using the opposite. We're using this length here, TB. We can use adjacent over hypotenuse, so you can use cosine or we can use sine. If we're using cosine, we're going to have to use the angle at T, and if we're using sine, we're going to have to use the angle at S2. So I'm going to use sine. So sine of 12, remember sine of theta is opposite over your hypotenuse, right? And if I'm using 12, opposite is the length that we're supposed to be getting there. So sine of 12 will be TB over our hypotenuse, which is the longest side, over TS2. So that TB is going to be equal to TS2 sine 12. TS2 is 270 sine of 12. And that works out to be 56 meters. All right, so this is just two questions you can practice using using the sine and cosine rule, as well as your trigonometric ratio rules. So take your time, do them, go over them, and try some other questions, and good luck in your exams.